Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video explains how normal quantile plots provide a more objective measure of normality. Let's get started. So, up to this point, we've actually been assessing normality subjectively. We make a histogram, we look at the resulting graph that it gives us, and we're trying to look for that normalized symmetrical bell shape to the data. And we can check for outliers with the histogram, but in some respects, that type of assessment is really subjective. And what we want is something that's more objective. And that's where the normal quantile plots come in. Essentially what we're doing is we're plotting a graph of points where the x values are from the original data, but the y values for our data points are the corresponding z-score from that individual data point. So the x value actually feeds in to that z-score equation to make a z-score, and so we can actually plot these points out, and the closer the points are to the straight line that you see here in red, okay, the more that the points adhere to the straight line, the more normal our data set is. Okay, that's normal with a capital N. It more conforms to a normal distribution. I could say it that way. Now, another name for this plot is the normal probability plot, because z-scores, with the normal distribution are all related to certain probabilities, and we're checking for normality. So normal probability plot is a name you sometimes hear for these plots. So keep in mind that the x values are random variables from your distribution. So whatever your data set is providing for you, the x values are coming from that. The y values are going to be the z-scores that correspond with those random variables. And these are the ordered pairs that we are plotting in the normal quantile plot. So how do we use this to evaluate for normality? Well, the first thing we're going to do is construct a histogram, just as we've always done. This allows us to see if we're even close, okay? Because if we're nowhere close to having a normal distribution, that shape of that distribution is going to be very, very different. If we see a clear departure from that bell-shaped curve, there's no reason for us to make the QQ plot or the normal quantile plot, because it's obvious that our distribution is not going to have a normal distribution. Once we have that histogram made, it's easy for us to look to see if there are any outliers in the data set. And typically, because the outliers can influence the shape of the distribution, if you've got more than one outlier in your data set, don't even bother going further. Just go ahead and stop here, because that QQ plot's not going to come out to show you a normal distribution. Of course, if you pass the first two hurdles here with the histogram and the outliers, then you can go ahead and construct your normal quantile plot. Again, the points must reside reasonably close to that straight line. I mean, how close is reasonable? Well, it's hard to describe, but you get better at it when the more you do this, the more experience you get, the more idea you get of what reasonably close is. The pattern of the points must resemble the pattern of a straight line, and you typically get that if they're going to be reasonably close to that straight line, though not always, but typically. So for a normal distribution, the points in a normal quantile plot are going to follow a straight line. So let's look at an example of what we're talking about here. So here's a histogram where the data is more or less normally distributed. It's not exact, but you've got that general bell-shaped curve. You don't really have any outliers here in the data set. And so the corresponding QQ plot is going to look like this. And notice how the data points there are reasonably close to that straight red line. That's kind of what you want to see when you're looking for a normal distribution. So we're generally following that straight line. Some points are closer than others, but that's the general idea of what we're looking for. If we have a uniform distribution, the points in the normal quantile plot will follow a sinusoidal line. So if we look at the histogram for a uniform distribution, we're going to get something that looks pretty much like this, okay, where all the different categories are occurring at the same frequency. This is a uniform distribution. It's got that box shape to it. If we make the normal quantile plot for these data, okay, here's what it looks like. So you've got a sort of a sinusoidal shape here because notice the S pattern that the points are making. So you're going below, above, and so it alternates as you're going from one side of that straight red line to the other. And that's the type of pattern that indicates you're looking at a uniform distribution and not a normal distribution. If our distribution is skewed, then our normal quantile plot will follow a curved line. So here's an example of a histogram where we're looking at some skewed data. And notice that there are no outliers, but we don't have that general bell shape because of the skewness in the data. So if we make our QQ plot from these data, here's what it looks like. Okay, notice that we've got a curved line. If you start tracing the general trend of the points that you're making, notice that you've got not a straight line, but it's like you had a straight line and then somebody put a bend into it. And so this curved line indicates that we've got a skewed distribution in our data set. And that brings us to the end of this lecture video. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.